Good day to Dr. Hafiz and everyone. I'm Connie from MEMS Group 20. Today I'm going to present about my project day, which is the results and discussion of my simulation on the proposed capacitive pressure sensor.
Good day everyone, I am Jocelyn Fei and this would be the presentation for Group 20, which is the simulation of pressure sensor.
For our group, we divided into two different membrane material, which is copper and aluminium as the flexible top membrane. The Young modulus of the top membrane of copper and aluminium that is used in the simulation are 117 gigapascal and 69 gigapascal respectively. The operation of the pressure sensor is when an input pressure is applied on a surface, it increases the deflection membrane and thereby decrease the air gap between the top and bottom electrode. Hence, it changing the output capacitance to a higher value. We applied three different input pressure on top surface of the membrane as in the figure 1. As a result, we observe the membrane reflection and output capacitance of the pressure sensor. Basically, silicon is used as the substrate, polysilicon as the bottom electrode, copper as the top electrode, and silicon dioxide fabricate in between of the top and bottom electrode. Different value of Young modulus and Poisson ratio has been used and manually key in the engineering data based on the material chosen. This is the result from the simulation by using static structural analysis. The applied input pressure ranged from 500 megapascal to 1.8 gigapascal, and it's showing a three different membrane deflection condition with output capacitance. The output capacitance is calculated using the formula taken from the journal. From the line graph itself, we can see that with the higher input pressure, the maximum membrane deflection or the deformation and the output capacitance is also increased accordingly. The maximum input pressure for copper is 1.3 gigapascal with a maximum deflection of membrane around 1000 micrometer. As the sensor reached the pull-in state, the top electrode merged with the bottom electrode as in the third result, and the air gap is zero at this state. It is proved that with a higher input pressure, a higher membrane deflection is formed, and thus the smaller the gap between the top and bottom electrodes. Consequently, it increased the output capacitance of the pressure sensor.
Before the simulation starts, the Young modulus of the materials need to be manually keyed into the engineering data, and the fixed support constraint must be applied to all top surfaces of every body part except the top membrane. In this project, the input pressure they use for this simulation is 500 megapascal, 950 megapascal, and 1 gigapascal. Here is the result of the maximum deflection of the top membrane of the device. It is measured in micrometer. As we can see, the maximum membrane deflection distance of the input 950 megapascal is 990.22 micrometer, which is near with the maximum deflection distance, which is equal to gap size distance 1000 micrometer. Hence, we can say that the maximum input pressure for the device is around 950 megapascal. If the input pressure is over 950 megapascal, the result the same as the result of 1 gigapascal will be formed, which is the top membrane is merged with the bottom electrode and the gap size is equal to 0. It means that the device is overloading and enter the pull-in state. Another output that have to be obtained is the output capacitance of the device. The output capacitance is calculated based on the maximum deflection of membrane by using this formula. As conclusion, the higher the input pressure, the greater the membrane deflection, the smaller the gap distance between two electrodes, hence the higher the output capacitance.
As in conclusion, aluminium has a lower pull-in state, which is around 950 megapascal as compared to copper, which is around 1.3 gigapascal. So, using different material will resulting in different value of maximum deflection of membrane due to the different elasticity or the Young modulus of the material, and thus it will resulting in a different output capacitance.
For the application of the capacitive pressure sensor in fight against COVID-19, first, it can be applied in the pressure monitoring system to measure the blood pressure of the COVID-19 patients. Next, it can be used with the hand pressing emergency button. The patients can press the button to ask for the medical support when they are in emergency. Last, it can be used with the automatic sliding door. The pressure sensor normally is high under the carpet in front of the door and people will step on it before enter the door. When the pressure is detected, the door is automatically sliding to open and close. With this sliding door, people can avoid to touch the handle of the door that usually has a lot of virus on it.
The usefulness of our design pressure sensor can be said that are able to fight against the spreading of COVID-19. And not only that, it also applicable in thousands of everyday application like a wearable watch that is used to call in emergency and assist the affected patients. That is all for our presentation. Thank you.